Okay, suppose that we own the right to this mine, okay, and we own the right to the mine for 2 periods. Each period is 10 years, so the total time horizon is 20 years, right? And we don't care about what happens after 20 years because maybe the world will be over, right? So our model, we just have a two-time period model, and our goal is to maximize the total social welfare in these 2 periods, right? Because we owned it for both period, and so it will benefit us, right, if we can also benefit from the future as well, right? So question is, what is the socially efficient Q1 and Q2? How much should we extract, right, in each period? Since we own the mine, we have an incentive to maximize welfare for both, right? Not maximize for each period, but just together, what is the total welfare for both? Okay, so we are considering a dynamic equilibrium, that is a market equilibrium that results when the present and the future cost and benefit are considered, right, compared to a static equilibrium. Couple more things we need to set up our model. One, there's a fixed value of resource that must be divided between the two time periods. Okay, so in this case, it will be 250 tons of copper. So we need to divide up between the 2 periods. Right? In our copper example, we're going to assume that the marginal net benefit in period 1 is equal to the marginal net benefit for period 2. Okay, what that means is the market condition is the same for each time period. Okay, and the total quantity is 250 units. All right, if the market condition is the same for both time period, that means then the optimal amount for each period, if the others are not considered, then it's 200 tons. So we can see that. We can see that here. Let's get a clear shot on what this graph means. So this is the so you notice here now I can graph both time periods on the same graph. And this is the reason why we needed to create this new equation, the marginal net benefit equation, right? In the beginning, so that we can talk about two periods together. Now this graph is similar to what we done, what we seeing in chapter 3 about the deforestation and the property rights allocation case, right, with the Coase theorem example. But so basically here, this axis is for marginal net benefit 1, and so when you want to read marginal net benefit for the first period, you go this way. You go from left to right. Right? And then what's convenient about this graph is, let's say that the first period consumes 150 tons. That means the second period will have consumed 100 tons, because the second period goes from right to left, right? And then this vertical axis on the right, right, that is the value, the marginal net benefit for the second period. And so the second period starts here. They start at zero, and a zero quantity, right? And then they come down this way. Okay, so the question is, where along this graph, right, should be the optimal allocation, right? Should we give the first period 100 and the second period 150, right, or another combination of? Okay, how should we maximize it? All right. Now, well, from the graph is obvious. From the graph, right, if you had to guess, obviously that's going to be the intersection. Okay, but let's think about why for a moment. Right. Let's think about why here, right? Now we can maximize total net revenue by maximizing the area under the both marginal net benefit curve. Okay, so the optimal condition is the marginal net benefit 1 equals marginal net benefit 2. Okay, but let's think about why that might be. So let's take a look at our, on paper here, right? So we claim, right, that total benefit is maximized when marginal net benefit 1 equals marginal net benefit 2. Okay. Let's think through this logically on why this has to be the case. Okay? For example, right, suppose that the marginal net benefit 1 is greater than marginal net benefit 2. What does this mean? This means that right now we're in around this location, right? That we're at this allocation so far. Now, in this allocation, right, when you allocate it this way, every ton that is given to the first period will generate more benefit than if reserved for the second period. right? Because the marginal net benefit is higher than the marginal net benefit in period 1 is higher than the marginal net benefit in period 2. And so if this is the current allocation, then then it's not optimal. Q1 should increase because you give more to the current period, and Q2 should go down, right? We should give less we should save less for the second period for the future. Now suppose that then the marginal net benefit for period 1 is less than the marginal net benefit for period 2, right? That means we're over in this allocation. We're in this area of the graph now. So that means for every ton that the first period is consuming now, it will be better off overall if we conserve that and save it for the future period, for the second period. And so if this is the allocation, then it is not optimal. Then Q1 should decrease and Q2 should increase. Right? We should consume less today and save more for tomorrow. And so at the optimal, right, at the optimal amount, then we know we know that Q1 not equal, excuse me, do say that, and Q2 star must be optimal. Okay. Now in this simple example, right, since they cross and since marginal net benefit 1 equals marginal net benefit 2, let's convert that into their mathematical equations. That means 100 minus 0.5 Q1 equals 100 minus 0.5 Q2. Okay, simplify this a little bit, cancel that, and then we get that Q1 star equals Q2 star. Okay, now if they're equal to each other and there's 250 tons, it must be that Q1 star equals 125 and Q2 star equals 125, right? We're going to divide this evenly in half. Okay, so that is the optimal. Okay, now of course here this is in the second period, and we did not discount it. Okay? This is a simple example. We haven't discounted yet, but of course, $1 today is not $1 received today is not the same as $1 received tomorrow. Okay, so we want the present value of copper extracted for both period not to be the same. Want both period to be the same, not the future value. So we must discount the marginal net benefit in the second period and set the present value equal to each other. So this is the real optimal condition that we want to consider.